Welcome, Chem 1. At this point in time, we've talked about how electrons are transferred from the cation to an anion to make an ionic bond. Today, we're going to show you the quicker way to come up with a formula of an ionic bond. Let's get started. Let's start by laying down some ground rules. First, we always write the cation, the positively charged ion, first. And then when we pair it with an anion, we have to balance out the charges with the correct number of cations and anions so the overall charge of the formula is 0. And finally, we should always check to make sure our formula is an empirical formula, which means it's the simplest ratio. So you would never have 2 cations and 2 anions because that can be reduced to 1:1. So in general, the process for this is to write the cation and its charge and write the anion and its charge, and then crisscross the charges because those charges will become the opposing ion's subscript. This is based on the work we've done in earlier units about electrons and how many are transferring to the opposing ion. During this process, you may see polyatomic ions. Those polyatomic ions can be found on the back of your periodic table. There's a list with cations on the left and anions on the right. After you crisscross those charges, you may need to simplify. But there are certain things on your polyatomic ion list that we don't simplify. Those 3 things are mercury 1, peroxide, and oxalate. These 3 polyatomic ions have even numbers within the polyatomic ion, and we've never reduced past that point. We'll give you some examples to help you clarify that. There are some things that are not on your polyatomic ion list, which are the elements. You are required to know the elements based on the column that they're in. At this point in time, we've talked about how everything in the first column has 1 valence electron, will lose that 1 valence electron, and make a +1 charge. Everything in the second column is a +2, scandium is a +3, titanium is a +4, and then we skip the rest of the transition metals and move on to boron. Boron's +3. The carbon family can technically be a +4 or a -4. We won't see a lot of ions that come from the carbon family. And then we get to our nonmetals. Nitrogen family -3, oxygen family -2, and finally the halogens would be a -1. Noble gases don't form charges and they're not going to show up in our ionic formulas. Alright, so let's do a couple examples here. The first one we got here is sodium and bromine. Sodium is in the first column of the periodic table, so it's going to be Na+1. We're going to write our cation. Bromine is in the halogens, so we're going to write Br-1. You can probably already tell that we need one of these to get an overall charge of 0. But if we're doing the crisscross method, we would take this charge here and make it the subscript of bromine, and we'd take this charge here and make it the subscript of Na. Preliminarily, we might write this, Na1Br1, but since they're both 1, we don't need to write them, and we can just write NaBr. The next one is potassium, which is in the first column of the periodic table, and oxygen, which is in the oxygen family, which has -2 charge. Now, when we crisscross, the 1 becomes the subscript of oxygen, and the 2 becomes the subscript of potassium. So this would be written as K2O. Next, we have aluminum, which is a +3 based on its column, and we have chlorine, which is a -1 because it's in the halogens. We would crisscross, the 3 becomes the subscript of chlorine, and the 1 becomes the subscript of aluminum. Notice we do not include the positive and negative charge when we're writing the formula. The subscript is just a number telling us how many of those we need. And if you look at this logically, you can see how if aluminum's a +3, we're going to need 3 of these chlorines to balance it out. And that's why the crisscross method works. Let's try one with a polyatomic ion. Ammonium is not on your periodic table. You would need to look at your list of cations and anions. And if you do that, you would see that ammonium is NH4 and it has a +1 charge. Sulfur, based on its column, is a -2. So now we need 1 sulfur, but we need 2 ammonium ions. Well, how do we write that? The way we write that is by writing the polyatomic ion NH4 and then putting the whole thing in parentheses. You put a 2 afterwards, and then we write our 1 sulfur. Anytime you need more than 1 polyatomic ion, you're going to need to put it in parentheses. Let's try another. Iron 3. Iron 3 is on your polyatomic ion list, but since that 3 is there, you should immediately know that it's a +3 charge. Anytime you have a Roman numeral after, that Roman numeral is telling you the charge of that ion. Sulfate is on your polyatomic ion list and is SO4, and it has a -2 charge. So now if we crisscross, we're going to need 2 iron cations, and we're going to need 3 sulfates, which means we're going to put sulfate in parentheses, and we're going to put the 3 on the outside, showing we need 3 of them. Potassium is a +1. Carbonate is a polyatomic ion that's on your list, and it's a -2. So we would crisscross, and we get K2CO3. Here's some other examples of formulas we could write from other elements. On this slide, there are a couple things to take note of. First of all, over here on the right side, you see that this is peroxide. If you look up peroxide, it is O2 with a -2 charge. Because of that, we don't reduce past O2. Peroxide is defined by it is O2, so we can't reduce past that point. In this last one, we have 2 peroxides, so we can reduce to 1 peroxide, which is what's happening. Same thing over here. We get 2 coppers and 2 sulfurs. We can reduce that to 1 of each. So in general, you can reduce down to the point where you have 1 of something. You just can't reduce peroxide, mercury 1, and oxalate. Here's other examples showing mercury 1 as Hg2 and oxalate as C2O4. Notice that we can't reduce those. On the ones to the left, magnesium's a +2 and nitrogen's a -3, crisscross. Scandium's a +3 and oxygen's a -2, and that's why we crisscross. Another thing you'll run into on the polyatomic ion list is ion variations, or a series of ions. Often within a series, we use prefixes and suffixes to tell us how many oxygens there are within that polyatomic ion. If we take a look at the chlorate family, we can look up chlorate on our polyatomic ion list and see that it is ClO3 with a -1. If we put per in front of chlorate, what that's telling us is we're going to add 1 more oxygen to that ion, but the charge will stay the same. So perchlorate is ClO4 with a -1 charge. Chlorite will always have 1 less oxygen than chlorate. So ClO2. And then if we put hypo in front of chlorite, we get the least amount of oxygens within the series. So the pattern kind of looks like this. You have per8 at the top, and then the suffix 8 by itself, the suffix ite by itself, and then hypo, and then the suffix ite go at the bottom. This could theoretically work for any series. For instance, sulfate is SO4 with a -2 charge. So immediately you should know that persulfate would be SO5, -2 charge. Sulfite would be SO3, -2 charge. And hyposulfite would be SO2 with a -2 charge. So all you have to do is identify what you know based on your polyatomic ion list, and then theoretically you should be able to work up and down the series based on what prefixes and suffixes are present. So here's strontium. Strontium is Sr+2. And then it says perphosphate. And you might be thinking, well, that's not on my list. But phosphate is. Phosphate is PO4 -3. So we know that perphosphate would be PO5, 1 more oxygen, with a -3 charge. We'd crisscross that, and we'd get Sr3, PO5 in parentheses, and then the 2 on the outside. Ammonium is NH4 with a +1 charge. Hyposulfite. Well, sulfate is SO4. Sulfite would be SO3, which means hyposulfite would be SO2, and those all have a -2 charge. So if we crisscross, we would need 2 ammoniums, and we'd only need 1 hyposulfite. And there's your formula. And there's the cleaned up version. And here would be answers of aluminum and carbonite, and copper 2 and borite. Carbonite's not on your polyatomic ion list, but carbonate, CO3, is. And borite isn't on your list either, but borate, BO3, is. So the idea is you can use what you know on your list to come up with these other polyatomic ions based on the series. I know we went through some of those examples quick, but we just wanted to give you the basics so you can start to practice this on your own. This is going to take a while for you to make sure you're getting the process done correctly. Do the activities. Make sure you're putting in the time so that you really understand what's going on. Keep up the good work. We'll see you next time.